Okay, now let's define the rational numbers. And the method is very close to the way we defined the integer in the previous chapter. The only way, the different ones, is the way of defining these ordered pairs. Okay, but let's see the reason why we need this one. Up to the integer set we defined in the previous chapter, the set of integer is closed under addition, subtraction, and multiplications. Okay, through the homework you already kind of taste those stuffs, but it's not closed under division, which means, for example, 2 divided by 3 is not a member of the integer set. So we are in need to develop a new number system which is closed under these 4 operations: addition, subtraction, multiplication, and division altogether. And within that system, actually, we can have all the natural numbers, integers, right, and positive, negative, including 0 altogether. Okay? So this is how we define it. Now, when you look at the beginning of this concept, it's very close to our previous ones, right? The difference was, in the previously, we have ordered pairs m and n, and these mn's are natural numbers, right? And there's no other kind of conditions whatsoever. And now, in this set y, no meanings of x and y's, we just want to separate them. Y is also a set of ordered pairs, but each coordinate's value is integers. Okay? So it includes positive, negative integers, including 0. So one possible case is like a 0, 0, right? But we don't want to accept that case. So the q cannot be 0. Not only 0 over 0, we don't accept 2, 0 or negative 3, 0. All those things, right? So the second coordinates of this new system doesn't allow to be 0. And because it's just ordered pairs right now, so you can define it like just ordered pairs of P and Q, like that, right? Same conditions like that. And Q cannot be 0, like this, but it's also possible. But the reason that I put this notation instead of parentheses is I want to separate these two notations, right? So from now on, just for discourse between you and me, if I'm writing down mn and it's like that, right? Then that is for an integer, right? But if I write down this way, then that is a rational number. It's a quotient. Okay, so actually, that is n minus m. Do you remember, right? How much we need? Okay. So that is k, right? So it's an integer. For this one, it's actually m over n. That will be our notation, our symbol for that. So big difference between those two notations, and that's why I want to separate them by this notation. So I don't need to say this is a rational number and that is an integer, okay, anymore. Just the notation itself, which one is which. Okay, so please keep that on your mind. Now we want to define a relation, okay, here. So we will just use same relation notation, but it's totally different. Okay, but whenever we want to say two elements in this set, which are the ordered sets, as a relation each other, if and only if, when you look at the outside ones and multiply them, must be equal to the product of inner parts of these two ordered pairs. Okay? And as you can see here, if later we are going to define like that, the notation for that set is m over n. Then PQ, okay, has a relation with P prime Q prime, means P over Q has a relation with P prime over Q prime. And that one looks like P times Q prime and P prime times Q prime is cross product. That's usual calculation between equal, right? So whenever we got PQ prime, P prime Q is equal, meaning is as a quotient form, these two notation must be equal, right? That's the relation here. Okay? So I think it's a very natural way. So we could kind of take a partition of this entire set, the collection of ordered pairs of integers, into that equivalence classes, and same notation like that, right? Y slash by that relation. Then this collection of equivalence classes is called the rational numbers. So meaning is each of these notation, technically with the bracket around it, is one single rational number. And this is just one representative of among all these possible cases, right? We are going to see that a little bit later. So from now on, remember like x with separate by that relation as that notation, right? Same thing for this ordered pairs and take the partition with that new relation, then that is denoted by that boldface capital Q. It's initial for quotient. And once again, be careful about all the given extra conditions of it. Now, one of the properties in rational numbers, like 12 over 4, right? Let's say 3. Let me say 15 over 6. Let me say that. And that rational number is 3 times 5 and 2 times 3. So let me write down this way. So 5 times 3 and 2 times 3. So it's same as 5 halves, right? The reason is because these two quotient, the rational numbers, belong to the same equivalence class according to this definition, right? So when you multiply them, it's going to be 15 times 2 and 5 times 6, both of them as 30, right? So they are equal, which means 15, 6 has a relation with 5 half, which means that inside this 5 half, that let me say like a 15, 6 is an element of this entire set. So you can choose either way, right, as a representative. So this one is same as 15, 6, right? Doesn't matter which representative you choose. But this might be the simplest one, and we call that is the lowest terms in quotient form, right? I have to cancel out common factors, right? So it's really happening in our quotient form, right? In our system, right? And this notation represents those cases. So whenever we use pk, qk as a representative, we can change that one to a lower forms, right? Like a pq forms, right? So to denote, we are going to use those quotient form as the symbol of it, right? Okay, so this one can be written by 5 half, right? And this one can be written by 15, 6, right? As we use. Say this. Okay, then let's confirm that case up. But before that, let me show you this case. In the previous case for integer, we are dealing with only natural numbers and natural numbers, right? So 1, 2, 3, and 1, 2, 3 only, right? Like that. So we have these grid points on this Cartesian coordinate system, and our partition looks like this diagonal collection of these diagonal points, right? Like that, and keep doing it. And this one represented by 0 and 1 and 2 and -1, -2, right? Like that. But in this case, we are dealing with integers, right? So to get this Cartesian coordinate system, we are having not only 1, 2, 3, but 0 and -1, -2, -3, 2, right? Same thing happens for here. So 1, 2, 3, and keep doing it. And -1, -2, -3, and keep doing it. Okay. So we have much more. We'll actually see number later. Grid points. Okay. So let's just focusing on these positive cases only. Okay. Then what is the meaning of the collection of this order pair PQ? So let me just choose 1, 1, right? So what is the order pairs belong to that 1, 1. Then we are looking for P over Q the same as 1 over 1, right? Or more officially, we have a relation with P over Q, which means 1 times P equals 1 times Q, right? I mean the outside one, so if you follow the order even, then 1 times Q equals 1 times P, right? Which means what? P equals Q, right? So 1, 1, 1, 1, 2, 2, 3, 3, 4, 4. Yes, they belong in the same equivalence classes, and that can be written by 1, 1 representatives for that. Now then, be careful about the next one. In the previously, when you choose 1, 2, we choose those diagonal grid points. But in here, for that 1, 2, what belongs to this? The first one, yeah, it's kind of 1, 2. Okay. But the next one is 2, not 3, right? That's here, but it should be 2, 4. It's kind of same ratio. So 1, 2 comes with 2, 4, not this one. So it's kind of going this way, right? And we are going to have a bunch of leftover points between these two equivalence classes, right? So 1, 3 goes like that, and we are going to have a bunch of leftover points between these two, like that, exactly, right? And that one is 2, 1, then it goes to 4, 2, right? Okay. In this case, no, careful. Sorry. So let me choose 1, 2, and let's see what happens. 2, 1, I'm sorry. What happens for 2, 1? That has 2, 1 first, but the common ratio, so it's going to be 4, 2, right? It's going to be flip that forms, right? So 4, 2 is here, so like that. So when you compare this portion and that portion, it's kind of mirror image by this, right? But the symbol for that is 1, 2 is 1/2, right? And symbol for that 2, 1 is actually 2, right? And 1, 1 becomes 0. Oh, is 1. Okay, so you see, and when you look at these missing points, like how about 2, 3, then there is 4, 6, right? And 3, is 2/3, right? So there's no points for 3, right? So 4, 6 only. So you can collect those again, and the represent for that is 2/3, right? So we are going to have a bunch of those collections like that, right? Now, that's only 1/4 of the entire Cartesian coordinate system. How about this negative case? Then we already know, like when x equals the y equals 0, we don't accept it, which means we are not thinking of the points on here, right? The y coordinate becomes 0. We are not thinking about it. So starting from -1, -1, right? And when you look at these diagonals, this also belongs here, right? Because that is not only collecting 1, 1, but how about negative 1, negative 1? The ratio is the same, right? So combining these two diagonals together becomes actually this, right? Not only that, not only one of these. Then you have a mirror image of it, right? For example, like this 1, 2, the mirror image is negative 1, negative 2, right? So we are going to have mirror image of this by the origin, right? It's kind of symmetric by the origin. You can collect all these bunch of stuff. Then combining these together, these mirror images together becomes that. So this set not only containing one of these, but containing the mirror image of that by the origin. And so far from here, as a big picture, the middle portion, this collection of these points becomes 1, right? As a representative. And this portion and that one, like 1, 2, like this, putting these together, the representative is 1/2, right? So 1/3, 1/4. So you're going to have all that rational number between 0 and 1 here. And all the integers, or not integers, greater than 1 portion is here. So this is less than 1, this is greater than 1. All the rational numbers. And whenever you think one group, there is always mirror image over there, right? So collecting all together is making that equivalence class. Then what happens for these two, second quadrant and fourth quadrant? Actually, they are dealing with negatives, right? So when you think, let me choose this one, mirror image of that over here by the y-axis, and its mirror image by the origin, right? So only this. So if the representative of this portion is 1, then this one can be written by negative of that symbol. Okay, so here that point is negative 1, 2, right? So the representative for that is going to be negative 1 over 2, negative 1/2. So this one, the mirror image of that by the y-axis, and its mirror image by the origin, so collection of those will be negative 1/2 for its representative of the symbol. And follow me? So we are going to have a bunch of those stuffs like that here and there. So there is no missing points, no missing grid elements, whatever. Is well separated as a disjoint class, and each one of them has its own representative. So this is kind of graphical way of explanation of what is the rational number according to this. Okay, then let's look at the calculation. Now we understand what is the meaning of that, right? But let's just calculate. Okay. So according to this, these numbers, the integers, are actually those coordinates values are integers, right? The only condition is the y coordinates cannot be 0. That's the only condition when we can put any number in it. Okay. So let's look at p, negative p over negative, just q, right? The middle ones, let's just check that one. Then that's the representation, it representing that this equivalence class negative p q, right? Then according to our definition, this one is the set of any how can I say, just p prime, okay, p prime q prime, right, as an order pair, and this p prime q prime has a relation with that, right, like that. But the meaning is like this way, so it must be like a negative p times q prime equals q times p prime, right? So it can be changed to collection of, we can change like, let me write down one more time, negative p times q prime equals q times p prime, right? Then that means is a p times q prime equals negative q times p prime, right? So this p prime q prime doesn't have any negative, right? So it's only p prime q prime. So it can be represented by pn negative q, right? By the definition, and it can be represented by p over negative q. And can you see the power of this? We only have one simple definition of how to collect those ordered pairs, right, within the same equivalence classes. Then by using that, we can show why we can place this negative at the numerator or denominator whenever we need it. We got the same number. That's the meaning of it. And because of the same reason, we can also prove this case too. And to show that relation, we need actually the definition of addition and subtraction and like that, right? So I'm going to show this one in the next video. But before going any further, I need some correction here. I mentioned that like in this Cartesian coordinate system, we don't include this one, right? But it's not actually. Look at here. The nature of this portion is x coordinates is 0 and y coordinates is y values, right? It's okay because when you take that one as a represent is 0 over y, which is 0, right? So those points are for that 0, right? Collection of those becomes 0. Okay? But these points, the coordinates of this point is x, 0, right? Second coordinates is 0 case, which we cannot accept. So removing this one from that Cartesian coordinates is necessary to develop these rational numbers, right? So careful, I'm sorry, not the y coordinates, but x coordinates. We have to remove it, and the collection of these y points on the y coordinates except 0 should be represented by 0. Okay?